Okay, so let's talk about Qualcomm and SystemReady, two things which, to be honest, if you'd asked me 2 years ago, I wouldn't thought would be on the same slide. Um, so I guess tiny bit about me. I work on Linux kernel and U-boot at Linaro as part of the Qualcomm services team. And outside of that, I also work on this project called Post-Market OS, which you can give it a Google. You can follow me on Mastodon if you want. So, SystemReady is not a super exciting topic in general. I mean, the whole point is that your bootloader should just work and get out the way, and you can just run whatever OS you would like, really. That's kind of the point. You need EFI apps to just work, and you also need to have a device tree that makes sense and can be consumed by normal Linux distro or ACPI. But in our case with IoT, it's definitely going to be device tree. So doing SystemReady is, well, we'll get to that in a sec, I guess. Qualcomm platforms, not very SystemReady, at least historically. The main sort of priority for Qualcomm has always been mobile, and other units like IoT tend to kind of, they have to take what they can get from mobile. So this has meant that a lot of Qualcomm IoT boards ship with an Android bootloader, which isn't very system ready. These are some of the things that we have to kind of deal with. Modifying the bootloader is fairly non-trivial and can't really be done in all cases with just open source code, but this is something that's kind of a pain point that's hoping to be addressed in the future. But yes, not very standards compliant. However, this is definitely changing. Obviously, I've been working on SystemReady for Qualcomm, and with new Qualcomm IoT platforms going forward, they're going to ship with EFI available out of the box, which is pretty amazing development. And that EFI will be EDK2 because that's what Qualcomm use. However, in the meantime, we've had a bunch of Qualcomm boards that are already out there in the wild that we need to somehow deliver SystemReady on. And that's where U-boot comes into play. So yeah, I mean, with EDK2, you tend to have issues trying to make this really generic and expandable due to how it's designed, whereas U-boot can consume a device tree just like Linux can. So, U-boot, it's simple, it's single-threaded, polling only. It runs device tree. And in our case, on Qualcomm, we're using the same device tree as Linux. It also has a very, its driver model is very reminiscent of Linux. And a lot of U-boot drivers are more or less straight ports from Linux. It has a lazy probing for devices. So when U-boot starts up, it doesn't actually probe drivers until you need them, which means it, well, should be fast and simple where possible. And it has this pretty amazing EFI framework, runtime implementation. Enough EFI for SystemReady. So, U-boot bring up on Qualcomm. One of the big issues that we had is DMA, particularly on the USB controller. Normally, you just allocate some memory, you program that memory address into the controller, and then it can access it. However, for various security reasons, and well, lots of reasons, you need an SMMU in the middle, which is responsible for letting you restrict what parts of memory the controller can access, and a whole lot of other very complicated things, I guess. And in most platforms, you can more or less just disable the SMMU. You configure bypass mode for the specific ID of the device, and it just kind of works. However, on Qualcomm platforms, the hypervisor actually protects some SMMU registers. One being the register where you, I forget the name of it, where you configure the mode. If you try to configure a context bank in bypass, then it will intercept that and it will configure it as fault instead, which means that then when the USB controller attempts to access memory, it causes a fault, and that fault is caught in EL3, not in EL1, so the board resets, which is not fantastic. However, once we figure this out, we're able to work around this by just configuring an identity mapping translation, and everything works. This also was needed for UFS, and now we have USB and UFS all working in U-boot. As I mentioned earlier, we are also using OV upstream. When I first got involved in this project, we were using a device tree from, well, nowhere really. It was completely homegrown device tree specific to Qualcomm U-boot that wasn't really compatible with bindings, and it wasn't great. However, thanks to Summit Garg, who put a big effort in importing device rebasing into U-boot, and a whole lot of work to get all the drivers moved over, and we are now just using Linux CT, which has the big side effect that supporting new devices in U-boot is usually really easy because you already have the device tree from Linux, so you just pull it in. At most, you maybe need a driver for the clocks and maybe pin control, and everything else mostly just works. So one cool feature of U-boot is this LMB allocator, which you have likely heard of if you're one of the older kernel developers, I guess. And it solves this surprisingly frustrating problem where, for some reason, so many boards in U-boot decide to just hard code all the load addresses. I mean, I guess this makes sense, but in our case, on Qualcomm, we want to have a single U-boot binary where we drop in our device tree and it just works. And so this, finding a way to dynamically allocate all the load addresses was more or less a requirement, and with LMB, we're able to do it. So, overall, Qualcomm support in U-boot needed some cleanup, but things are looking pretty great now. Everything is handled at runtime, so we don't have any hard-coded memory layouts or addresses, and you can build one U-boot binary and run it on any board you like. There's been some interest from the community, so the MSM 8916 mainline project have looked into this with the idea of being able to run distros via EFI rather than the current mechanism of they use ext Linux, I think, from LK. So yeah. So, SystemReady. Once you have U-boot support, U-boot implements EFI, and as long as all your hardware works correctly, SystemReady is kind of there for you. Maybe one or two minor hiccups along the way, but that's mostly it. So right now, the RB2 platform is SystemReady IR compliant and in the process of being certified. You can download latest U-boot master, build it for the RB2, and then download Fedora Rawhide, plug it in, flash it to a USB stick, and it'll boot up on the board. which, yeah, it's been a lot of work to get here, but nice to see it pay off, I guess. Sorry, I realized I didn't explain what the RB2 actually is. So the RB1, 2, 3, and 5 is this stack of robotics, Qualcomm robotics boards. They're kind of reference platforms for people to develop their products on, more or less. So you can use this to assess, can Qualcomm boards do what I need them to do before I go and start designing hardware around the board. So the RB2 is kind of right in the middle there. It's on the cheaper side, but we're planning to bring up the RB1, 3, and 5, get them done too. So overall, upstream U-boot status, we have all of these SoCs and hopefully more to come. They can all, at the very least, boot to a U-boot shell. A bunch of them can boot from USB, and only a few of them have FC cards and eMMC support. This is mostly due to a small issue with device tree compatibility, where a lot of these devices reference a node called the RPM clock controller, and this is has some clocks which live on a coprocessor, which is very difficult to talk to, and we kind of want to avoid having to bring a bunch of drivers for this into U-boot. The fortunate part is it's not actually needed in order to boot. Its job is mostly around, well, resource power management, which is relevant when you're booted into an OS, but because by default, by the time we get to U-boot, it's already been initialized and the resources are already allocated for us, we can just kind of ignore it. So we need a stub driver in U-boot, essentially, to say, to allow us to skip that and still provide some kind of clock controller for the devices that think they need it. So all of these additional features, like capsule updates, have been implemented and are pending upstream now. Yeah. So the future, something I really want to see is wider community adoption. I think particularly on some of the production devices that people already have, being able to run U-boot and have an EFI interface is something that will really help us out in the long term. Another thing that I'm very interested in is LVFS, and if we can find a way to provide U-boot firmware images for these boards via LVFS and let people actually get bootloader updates using the capsule update mechanism. So we can have some kind of support there. And of course, the docs always need improving. Yeah, I guess I kind of did a bit of a speed run on this one. So that's all. Thanks a lot. Questions? Yeah, of course. Question over here. Thank you.
Sorry, great talk. Can you tell a little bit more about LVFS, what that is, and where you want to use it?
Yeah, for sure. LVFS is the Linux vendor firmware service. So it is a repository for vendors to be able to upload firmware for anything from bootloaders to like fingerprint readers. And it has a tool called Firmware Update, which is shipped on all major Linux distributions, usually installed by default. And it uses a few different mechanisms to figure out if you have any peripherals that can be updated, or if the device itself has a bootloader which can be updated via LVFS. So it's a way for vendors to ship firmware updates to Linux users without having to care about distro packaging or any of this complexity. They just upload their firmware to LVFS, and their users receive it via firmware update. So in our case, this lets us develop new features in U-Boot and make them available to the upstream community without having to manually install new firmware.
So, sorry, I still have the mic. What about loading firmware in U-Boot? Do you not need to load a few of the Qualcomm peripheral firmwares?
No. So if we, so currently the way that we boot U-Boot is chain loading via the Android bootloader. This is kind of for a proof of concept and initial bring up. But I hope that we're able to switch over to a model where we actually can replace some of the first stage bootloader. This will make booting faster and even simpler and all of this. But no, all of the firmware that needs to be loaded gets loaded by the preloader.
So you mentioned earlier that there is a plan to move to EDK2 for the Qualcomm platform. So does that also include the RB platforms, or?
Yeah. So I'm not exactly sure how much of this is set in stone yet. Sure. So as I understand it, the next gen RB3 Gen 2, which you can now order, but will probably be a while before you get it. It will ship with EDK2 like all of Qualcomm's previous devices do, and it's moving away from the mobile model where there is this Android bootloader, which is just an EFI app, which it will always run. It's embedded in, and you cannot actually run like EFI shell, for example, over to a model where there's an ESP, and they've, I believe for the reference images, they plan to use systemd boot, and so it's more of a standard EFI. However, it's still based on the downstream EDK2, which they ship and is not yet open source.
You probably heard from Linder at the keynote. So the platform he talked about was Qualcomm. It's part of the Qualcomm Linux. So yes, it doesn't have any Androidisms. We're trying to get rid of that. And as part of that, it's coming with EDK2 and systemd boot. And over time, we plan to get that as well, SystemReady compliant. So that's the plan.
Yep.
Thanks for the talk. Can you tell us a bit more about the problem regarding capsule update, please?
Yeah, so capsule update is implemented via this generic mechanism in U-Boot. So during boot, we need to, in the Qualcomm generic code, there's a table of firmware images that can be updated, the GUIDs for those images, and the names and stuff like that. And then during boot, because we have to do this at runtime on Qualcomm, we generate a DFU string, which is basically telling U-Boot's DFU interface where to flash the image. So in our case, to UFS or eMMC into one of the boot partitions, because Qualcomm platforms are A/B, so we need to figure out whether we're on the A slot or the B slot, and which partition that corresponds to. And so we set this DFU string, and then U-Boot is configured to check for a capsule update during boot, and if it finds one, then it will flash it using this DFU string. There's a larger issue around EFI runtime support, set variable at runtime, which is why we need this kind of workaround in U-Boot. In the vast majority of cases, it isn't possible to set EFI variables directly from runtime because the EFI runtime can't access storage in order to save those variables, and we don't have any SPI flash or something. Does that answer your question?
Yes, thanks.
Great, thanks.
Do you plan on implementing any support for DFU of internal flash in any of the boards?
So that you could use a DFU interface over USB?
Yeah.
Yeah, I'm not sure exactly what's needed for that to work, but it's probably not very much effort to integrate.
So this will still pass control at EL1?
Yes.
Okay.
For
So
now.
this, okay. So any plans where control can be passed in EL2? If somebody wants to load a custom hypervisor.
It's not on the roadmap. The issue with so I've tested this, and the issue with passing control on EL2 is that Qualcomm platforms rely pretty heavily on the hypervisor for hardware initialization. So all of the DSPs that you need to boot up, the Linux drivers as they're implemented right now rely on the hypervisor to do a lot of that for it. And it is possible to make them work anyway. For example, the Chromebooks all run in EL2, and if you look at the drivers for them, they have a lot more stuff going on because they have to actually manually boot the DSP, whereas in Qualcomm it's handled by the hypervisor. This is definitely something I think it would be great to see more of, but we're quite a ways away from that being something that's particularly useful. Okay. Great. No more questions? Thanks.